So valid parentheses. Given a string s containing the characters, like just brackets, basically, determine if the input string is valid. An input string is valid if open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. Every closed bracket has a corresponding open bracket of the same type, right? So like here we see some examples. So we have open parentheses, close parentheses. That's correct. Open, like you open them. If you ever open them, you have to close them before you close any other one. So an example of like a wrong one here is this one. Because we try to close the outside one before closing the inside one. Then that's incorrect. Or like this one, we try to close a bracket that we didn't ever open. Some edge cases to think about here is what if, for example, our input is this, just a closing bracket. Then we have to check, if we go to check like what was the last open bracket, we're not gonna see anything because we didn't open any brackets. So that's an edge case. Another edge case would be like this one that they show here, where you try to close a bracket before closing like one that goes after. That's another like important one. Let's think other edge cases. When you try to close a bracket that you never opened. It's very similar to the first one, but in this case we have seen a bracket that has opened before. So these would be sort of our edge cases. So how are we gonna do this? We're opening brackets. So what tells us if it's wrong, right? So here, it's wrong if we try to close. So we're keeping track of the brackets we've opened, and we care about the most recent one we've opened. So this sounds very similar to a data structure that is very popular in programming. It's called a stack. And if an easy word to think about is like if you have a stack of plates. Or like if you have a stack of plates, you put one here in your cupboard, then you put another one on top, then you put another one on top. If you're gonna remove a plate, I mean, I guess you could remove them from the bottom, but the most normal thing, if all the plates are the same, is to remove them from the top, right? It's easier because if you try to remove them from the bottom, all the other plates might like fall and crash everywhere. So the most recent plate you put in is the plate you take out, right? You have like a stack of plates. Same with our parentheses. The most recent parentheses we put in is the one we have to take out. If we try to take out a parenthesis that's in the bottom, everything's gonna crash, right? So as I've hinted just now, you can use a stack to solve this problem. So a stack basically does what we just said. So it just adds elements to, it can be an array in this case. So you add elements to an array, but then when you're gonna take out an element, you take out the most recent one you've put in. So the one at the, if you add them from left to right, the one at the right, and you take them out in that way. So you have two operations. You push an element into that array, and then you pop that element. And you can only pop the most recent one you've put in. You can't pop from here, from here, from here. You can only pop from the end. And that's just a restriction you put to be able to use this this data structure. So in this case, how are we going to keep track of the parentheses we've opened? So we're going to put them in a stack. When we're only going to put them in a stack if they're open ones, because once they're closing, then we can remove them from the stack basically. So in this case, let's say this is our string. So we open this one first. So we put that in the stack. Then we open this one. So we put that on the stack. Then we open this one. So we put that on the stack. Okay. And let's say we now try to close it. So let's do a proper one first. So this is a proper string, as you can see. So we go to this next one, and we see it's a closing bracket. So now you check the top of the stack. Is the top of the stack a matching curly brace? If so, we pop it, right? So if the last brace we opened is of the same type, then good. we can get rid of these two. We don't have to worry about them anymore. So we just do that. We remove it from the stack. Now you go into the next one. There's a close bracket and it matches. Okay, so we remove them from the stack. Then there's, we just did this one. Then there's this one. It has a matching one. Then we remove them from the stack. So at the end, you have to make sure to check, is the stack empty? Because if you have, for example, one brace that's just open, I think that's wrong. So if that is the case, you have to check at the end that there's no open brackets in your stack, because that means there were brackets that weren't closed, right? Another edge case you might have that I mentioned at the beginning is, let's say your string is just this, which I think is one of the examples. Okay, when you see this, you go to check, oh, what's the bracket at the top of the stack? And the stack is empty. So normally when you do that in C++, it gives you an error. It tells you like, oh, you just try to access an element that doesn't exist. So that's something you need to be wary of. You first have to check, is there something in the stack? And if there's not, then the string is invalid, basically. So we're gonna go through the string. If there's an open one, we add it to the stack. If there's a closed one, we check the top of the stack. If it's the matching one, good. We just remove the top of the stack. If it's not, then we have a problem and we return false because it's an invalid string. And yeah, that's what we're gonna do. Our stack is gonna contain a char and we're gonna call it stack. I just don't want to have to write a condition for every single type of bracket. So what I'm gonna do is create a dictionary for it. So an ordered map, and it's gonna go from a char to another char, and it's gonna be just a reference. I'm just gonna call it ref. It's gonna be a reference table. And so in our reference table, we're gonna say ref of this. We're gonna match a closing parenthesis to its matching one. So for the closing one in this one is gonna be this one. And then we'll repeat that 3 times. Our closing one for this one is gonna be this one, and our opening one for this one is gonna be this one. Okay, so now we go over the string basically. I wonder, you can probably, yeah, int I equals 0, I less than s dot length, I think, I plus plus. So now we check if si, let's say if ref.count si is 0. So that basically means if we have an open parenthesis, because the only keys we have in our ref are the closing ones. So if it doesn't see any on a ref, that means it's an open one. So if we see an open one, we're just gonna put it in the stack. So stack.push stack.push si else. So that means if it's a closing one, then if stack.size equals 0, then we're going to return false, because that means there's no opening bracket in the stack, so this closing bracket doesn't have a matching opening one. Otherwise, we check that if it's matching. So if stack.top is equal to ref of si, because we know that si is a closing bracket. So we're checking, is the top of the stack equal to the matching one? So first let's check if not. And if so, we're going to return false. So if it's not a matching one, we're going to return false. If it is a matching one, we're just going to stack.pop. right? And at the end, we return true if the stack is empty, because we don't want any opening brackets that don't have closing ones at the end. So we check stack, we return stack dot empty, right? So what this is doing, in case that wasn't very clear, is if we have the case of, like, let's say we open this and then we close this, or no, sorry, we open that and we open that. Technically, we're gonna be able to reach the end because we didn't find a closing one that didn't have a matching open one, but the stack is gonna have this open bracket at the end, right? So we need a matching closing bracket for this opening bracket. And if it just left at the end, then this is not a valid string. Nice. Cool. Hope. Let's go.